All right, welcome to 15.10. This is actually our first excursion into 15.10. We'll revisit it again in the last unit. Here we're doing change of variables in 2D for double integrals. So change of variables is a really important topic in calculus. You might remember from BC being able to do U substitutions, right? Where we were going, from some function of x or whatever to a function of u. And when we did this, right, we actually had some, a little bit of chain rule that we had to do. And we also changed our bounds. Well, it turns out that in multivariable, we're not just going from x to u. We're actually going to replace our entire set of variables. We're going to replace both x and y with two new variables that we're going to call u and v. And our goal is to be able to go back and forth between these two descriptions, just like with u substitution, in order to make certain integrals easier to do or possible to do. So what we're going to do is we're going to talk about transformations that look like this, that actually take us from uv space into xy space. And obviously we can go back. But for the moment, we're going to consider a transformation like this. And so we might have, for instance, a point here in UV space that's going to map to some point over here in XY space. And we can get there using our transformation. And we can get back, in theory, if this relationship is 1-to-1, by using the inverse of our relationship. And we've already seen a number of these things before, right? As an example you've already seen before, we have, if we know r and we know theta, we can go back to x and y using these substitutions. And obviously the substitution lets us go back and forth. So polar is one example we've already seen. And we refer to this these transformed points as images. And in fact, one thing you'll notice is that as you transform between x and y and u and v, actually the whole region of our integral will shift and morph. And this is kind of the counterpart of changing our bounds. Here, it's not just our bounds that change, the entire region changes. So let's look at an example of this. This is going to seem a little strange, but what I want to do is I want to look at this little unit square in u and v. So we're just going to mark out our unit square here. Here's our little unit square. Noting, of course, that this point here is 1, 1. And I want to actually see what does the image of this look like in x and y. What does the image of this look like in x and y under the following transformation? And our transformation looks like this, that x equals u squared minus v squared, and y equals 2uv. Now this might seem, by the way, please make sure to draw your u's and v's very carefully. Now this might seem a little intractable, but we can start by just transforming some things. So let's start actually with some points, right? Let's start with our 4 corners of our square. So if we look here at 0, 0, which is u equals 0, v equals 0. Well, if both u and v are 0, we should be able to tell, I'm actually going to put this down over here. Excuse me. We should be able to tell that 0, 0 just maps again to x and y being 0, 0. So this point goes here. If we check our corner at 1, 0, where u is equal to 1 and v is equal to 0, we end up also with the point 1, 0. So far, so good. Okay. What if we check the point 1, 1, which is, of course, the corner of our square? Well, if I plug in 1, 1, I get the point 1 minus 1 is 0, 2. So all of a sudden this point 1, 1 maps to the point 0, comma 2. Interesting. And if I go look at the point 0, 1, which is my last corner, this actually goes to negative 1, comma 0, which is over here. So we've gotten a start of how kind of these points have been transformed. This one has sort of come down over here. These two have stayed where they are, and this corner has moved up onto the y-axis. But to get a better look of exactly what the shape of our region looks like, I want to look at each of these 4 sides individually. So we're going to look at side 1, 2, 3, and 4. And I guess I will actually probably do these in different colors. So let's look at side 1 right here. What is side 1? Side 1 here is, it's on the u-axis, so this is going to be v equals 0 with u between 0 and 1. Well, if v equals 0, what I get is I get x equals u squared, and I get y equals 0. So this is going to be y equals 0, and x is going to be between 0 and 1. So as I move this way along this, I also move this way. Notice that it's x equals u squared. So if I'm moving at a nice constant pace in u, it actually, I start to speed up, moving along in the x direction. But so far so good. 0, 0 to 1, 0 stays the same. If I look at side 2, this is going to be u equals 1 for v between 0 and 1. Now if I look at this side, so here's the transformed image of side 1. If I look at this ends up with x equals 1 minus v squared, and y equals 2v. If I do a little substitution, right, y over 2, I end up with x equals 1 minus y squared over 4. This is a parabola that kind of goes, I'm going to try to draw this well. It's actually a parabola. So as I go this way along side 2, I end up with this parabolic motion here. Side 3, you might suggest from symmetry is going to be similar, and you'd be correct. This is going to be v equals 1 for u between 0 and 1. You end up with x equals u squared minus 1, and y equals 2u this time. And if I kind of put those together, I get x equals y squared over 4 minus 1, which is just the negative of this. So it should be symmetrical. Here's side 3. And I'm not going to prove it right now, but you might imagine that side 4, as I come down this way in side 4, we actually make our way back to the origin. And you'd be correct. So our square here in UV maps to this weird parabolic region in X and Y. So being able to transform these spaces is very useful. Now, and it's really just a matter of plugging in and being able to kind of observe how these equations and points shift around. I do want to note, right, obviously here we're going from UV over to XY. It's more often the case, right, we want to go the other way. It's more often the case that we start with a weird region in XY and we want to transform it into something nicer in U and V, right? That's the whole reason to change variables, is for your changed variables to be nicer. So let's ask ourselves this important question. How does this actually affect a double integral? So what we're going to do is we're just going to look at a small region of space in U and V and in X and Y, right? In X and Y. And what I want to ask is, if I have a little region in U and V, right? Let's say it's this little region delta U, delta V. I want to know, what does this look like when that little square is transformed in x and y. And specifically, I want to know if I can find the area of this transformed tile. Because what we're really doing here is figuring out how does the area change as we move from u and v to x and y, or vice versa. Well, it turns out that, if I kind of look at my transformation, and we can go a little bit more in depth into this in class. If I look at my transformation as being kind of what is my position vector in xy space given my initial coordinates uv? Well, I'll have some function of x that tells me what x is, and some function y that tells me where y is. So again, uv goes in, xy come out. It turns out that this area in general is probably not a square, but again, using calculus magic, we can approximate it using two little vectors. We can approximate this area. We can approximate this area. And in fact, rather than just using a and b, what we can do is find that we actually end up with two vectors, ru and rv. And we'll go a little bit more into the geometric nature of this in class. These are in fact partial derivatives. The partial derivative of r with respect to u, which is, partial x partial u plus partial y partial u j hat, and rv partial x partial v I hat plus partial y partial v j hat. And in order to find the actual area of this, we're going to need to scale these vectors up by delta u and delta v, because the bigger our original region is, the bigger our transformed region will be. And in order to find the area of this transformed thing, we're actually going to take this cross product of ru delta u cross rv delta v. And the reason we're going to do that is because, again, the cross product tells us this area. And if you're not entirely sure where these vectors come from, we will go over that. We will go over that in class. We will go over that in class a little bit more. We can actually rewrite this cross product in an easier way. We can pull out the delta u and delta v, and this ends up as ru cross rv, or the magnitude of ru cross rv, delta u delta v. All right, so let's go ahead and find that cross product. It turns out, and you can prove this to your own satisfaction, that the magnitude of this cross product, and I invite you to work it out, ends up looking like this. It ends up looking like the determinant, partial x partial u, partial x partial v. Oh, I'm sorry. Well, yeah, I'm jumping the gun here. I don't want to jump any guns here. Partial y partial u, partial x partial v, partial y partial v. And I'm actually going to rewrite this. I'm just going to take a transposition of it. I'm going to swap the determinant around a little bit. And I'm going to change, and I'm going to write it this way. I'm going to write it as partial x partial u partial x partial v. So all of our x's are on one row. Partial y partial u, partial y partial v, and all of our y derivatives are in the next row. And this is actually a really important determinant. This determinant goes by a special name, and this is called the Jacobian. And it goes by this notation of kind of partial xy over partial uv. and we end up with kind of this matrix, xu, xv, yu, yv. And the power of this thing is, notice that the area of this little section is the Jacobian times delta u delta v. And what that means is that we can actually rewrite our integral. If we start in x and y, right? If we have some function of x and y, dA, over our region R in the xy plane, we can turn this into an integral in the uv plane by, first of all, converting our integral to u and v. And then, like we saw in polar, we need an extra term. And that extra term turns out to be the absolute value of the Jacobian. That the Jacobian, partial xy, over partial uv, that the Jacobian tells us how to translate from one coordinate system to another. And just to do a quick example of this, we've already seen this work in class, right, with polar. What is the Jacobian for the conversion from x and y to r and theta? Well, it should be this matrix, the determinant of this matrix, xr, x theta, yr, y theta. The derivative of x with respect to r is cosine theta, with respect to theta is negative r sine theta. And then we get sine theta r cosine theta. If I actually take this determinant, I end up with r times cosine squared theta plus r times sine squared theta, which is to say the Jacobian of the conversion from xy to polar is r. And this is an alternative explanation from a mathy or change of variables background about why we get y dx dy turns into r dr d theta. The r is the Jacobian, that extra r is the Jacobian of the transformation from Cartesian coordinates to polar coordinates. So we're going to look at some examples in class of actually doing this. And in order, in general, to actually solve an integral like this, what you need to do is you need to, first of all, figure out how to transform your space, figure out what your Jacobian is, and then put it together to actually solve your integral. So we'll see a bunch of examples of that in class.